In the world of physics, few debates have been as intellectually stimulating and fiercely contested as the one between Albert Einstein and Niels Bohr. These two towering figures of science, each with their own unique perspectives and groundbreaking contributions, found themselves at odds over the very nature of reality. At the heart of this clash of titans lay a fundamental disagreement about the nature of reality itself. While both men sought to understand the universe, their visions of how it operated were starkly different. Einstein, known for his elegant theories of relativity, grappled with the implications of quantum mechanics, a revolutionary framework that described the behavior of matter at the subatomic level. His theories had reshaped our understanding of space, time, and gravity, but quantum mechanics presented a new challenge. The crux of his discomfort was succinctly captured in his famous declaration, "God does not play dice with the universe." This statement was more than just a catchy phrase. It encapsulated his deep philosophical belief in a deterministic universe. Einstein's statement stemmed from his deep-seated belief in a universe governed by order and predictability. He envisioned a cosmos where every event, no matter how small, was determined by preceding events, following a precise and unalterable path. He found the probabilistic nature of quantum mechanics, where chance and uncertainty reigned supreme, deeply unsettling. The idea that particles could exist in multiple states simultaneously until observed was, to him, a radical departure from the orderly universe he cherished. In the quantum realm, particles didn't follow predictable paths, but instead existed in a haze of probability waves, their properties only becoming definite upon measurement. This concept, known as wave-particle duality, was a cornerstone of quantum mechanics, but a thorn in Einstein's side. This inherent randomness was anathema to Einstein's deterministic worldview, where he believed that every event, from the smallest subatomic interaction to the grand motions of celestial bodies, was predetermined. He could not reconcile this randomness with his vision of a clockwork universe. The stage for this epic debate was set in the 1920s, during the tumultuous birth pangs of quantum mechanics. As new discoveries emerged, the scientific community was abuzz with excitement and controversy. The Solvay conferences, held in Brussels and attended by the era's leading physicists, became the battleground for this clash of ideas. These gatherings were more than just academic meetings, they were arenas where the future of physics was fiercely debated. Einstein, the elder statesman of physics, found himself increasingly isolated as a new generation of physicists, led by Bohr, embraced the probabilistic interpretation of quantum mechanics. Bohr and his followers saw the beauty in the uncertainty, viewing it as a fundamental aspect of nature. The debates were legendary, characterized by passionate arguments, thought experiments, and a relentless pursuit of scientific truth. These intellectual battles were not just about equations and theories, they were about the very essence of reality. While Einstein's skepticism towards quantum mechanics never wavered, his critiques, often presented as thought experiments designed to expose inconsistencies in the theory, proved to be immensely valuable. These thought experiments, such as the famous EPR paradox, challenged physicists to think deeper and more critically. They forced the proponents of quantum mechanics to refine their arguments and solidify the foundations of the theory. Each challenge from Einstein was met with rigorous analysis and often led to new insights and advancements. In many ways, Einstein's resistance, though ultimately unsuccessful in overturning the probabilistic interpretation, served as a crucible in which quantum mechanics was tested and strengthened. His relentless pursuit of a deeper understanding pushed the boundaries of science and left an indelible mark on the field. Einstein's staunch opposition to the probabilistic interpretation of quantum mechanics stemmed from a fundamental dissonance between his own theories of relativity and the emerging picture of the quantum world. This clash wasn't just a minor disagreement but a profound divergence in understanding the very nature of reality. Relativity, a cornerstone of modern physics, presented a universe governed by elegant mathematical laws where gravity warped the fabric of space-time. This theory, which had been meticulously crafted and tested, offered a deterministic framework, implying that the past, present, and future were all woven into the tapestry of space-time. In this deterministic universe, every event was a consequence of preceding events, and the future could, in principle, be predicted with absolute certainty if one had complete knowledge of the present. Quantum mechanics, on the other hand, introduced an inherent fuzziness into the fabric of reality. This new theory, which emerged in the early 20th century, suggested that particles, instead of following precise trajectories, existed as probability waves smeared out across space. The act of measurement, rather than passively revealing pre-existing properties, seemed to magically collapse these waves, forcing the particle to assume a definite position or momentum. This phenomenon, known as wave function collapse, was deeply unsettling to Einstein. This inherent randomness, where the outcome of an experiment wasn't predetermined but rather governed by chance, clashed head-on with Einstein's deep-seated belief in a universe governed by order and causality. He famously remarked, "God does not play dice with the universe," encapsulating his discomfort with the idea of fundamental randomness. The incompatibility between these two pillars of modern physics wasn't merely a matter of philosophical preference, it had profound implications for our understanding of the cosmos. If the universe was inherently probabilistic at the quantum level, did it mean that the future was fundamentally uncertain? Did it imply that even the most carefully constructed experiment could only yield probable outcomes, never definitive answers? These questions struck at the heart of scientific inquiry, challenging the very notion of a knowable and predictable universe. Einstein, deeply troubled by these implications, clung to the belief that quantum mechanics, while undoubtedly successful in its predictions, was incomplete. He argued that there must be hidden variables yet undiscovered factors lurking beneath the probabilistic surface, which, once understood, would restore determinism to the quantum realm. His quest for a unified theory, one that would reconcile the seemingly disparate worlds of relativity and quantum mechanics, became a driving force in his later years. This pursuit was not just a scientific endeavor, but a philosophical one, as Einstein sought to uncover a deeper, more fundamental layer of reality. Despite his relentless efforts, the unified theory remained elusive. The scientific community continued to grapple with the dual nature of reality, with some embracing the probabilistic nature of quantum mechanics and others, like Einstein, searching for a more deterministic explanation. These debates and inquiries have persisted into the modern era, driving advancements in both theoretical and experimental physics. The quest to reconcile relativity and quantum mechanics remains one of the most profound challenges in science, inspiring generations of physicists to explore the deepest mysteries of the cosmos. Einstein's legacy, marked by his unwavering commitment to understanding the universe, continues to influence contemporary scientific thought. His belief in an orderly, deterministic universe serves as a reminder of the enduring quest for knowledge and the ever-evolving nature of scientific discovery. As we continue to explore the cosmos, the clashing views of relativity and quantum mechanics remind us that our understanding of reality is still incomplete. The search for a unified theory, a single framework that can explain all physical phenomena, remains one of the most tantalizing goals in science. Though Einstein's quest for a unified theory was ultimately unfulfilled, his contributions laid the groundwork for future discoveries. The journey to reconcile these two pillars of modern physics continues, driven by the same curiosity and determination that defined Einstein's remarkable career. Einstein's unease with quantum mechanics stemmed not only from its probabilistic nature, but also from its apparent incompatibility with his revolutionary concept of the block universe. This concept, a direct consequence of his theory of special relativity, shattered our intuitive understanding of time as a flowing river, replacing it with a static, four-dimensional reality where past, present, and future coexist. Imagine for a moment a loaf of bread, its slices representing different moments in time. In the block universe, all these slices from the past to the future exist simultaneously, much like the entire loaf exists as a single entity. Just as each slice of bread has a definite position within the loaf, each moment in time has a fixed place in the four-dimensional space-time continuum. This implies that the future, much like the past, is already out there, pre-existing, and immutable. This static view of time had profound philosophical implications. It challenged our intuitive notion of free will, suggesting that our choices, our actions, and indeed our entire lives are already laid out before us, predetermined and unchangeable. This deterministic picture, where the future is as fixed and inevitable as the past, resonated deeply with Einstein's belief in an orderly universe governed by laws, a universe where chance and uncertainty played no role. However, the block universe presented a profound challenge to the probabilistic interpretation of quantum mechanics. If the future already exists, How can there be genuine uncertainty in the outcome of a quantum experiment? How can the act of measurement truly influence the fate of a particle if its future state is already predetermined within the block universe? These questions highlighted the fundamental tension between Einstein's deterministic worldview and the probabilistic nature of the quantum realm, a tension that continues to fascinate and perplex physicists to this day. To delve deeper, consider the implications of a pre-existing future. If every event is already set in the space-time continuum, then the randomness we observe in quantum mechanics must be an illusion. This deterministic view suggests that what we perceive as random outcomes are simply the unfolding of a pre-written script. This notion is unsettling for many, as it implies that our sense of agency and control over our destiny is merely a perception, not reality. The philosophical ramifications extend beyond physics, touching on existential questions about the nature of existence and the human experience. Einstein's vision of a deterministic universe was not just a scientific stance, but a reflection of his deeper belief in a cosmos governed by order and predictability. He famously said, "God does not play dice with the universe," encapsulating his rejection of randomness and his commitment to a universe where everything is determined by laws. Yet, the block universe theory remains one of the most intriguing and debated concepts in modern physics. It forces us to reconsider our understanding of time, reality, and our place within the cosmos. As we continue to explore the quantum realm, the tension between determinism and probability remains a central theme, driving both scientific inquiry and philosophical debate. The interplay between Einstein's deterministic universe and the probabilistic nature of quantum mechanics is not just a scientific puzzle but a profound mystery that challenges our deepest assumptions about reality. As we push the boundaries of our knowledge, we may one day reconcile these seemingly opposing views, uncovering a deeper, more unified understanding of the universe. Until then, the debate sparked by Einstein's vision of time and space continues to inspire and challenge, reminding us of the ever-evolving nature of scientific discovery. The quest to understand the true nature of time and space is far from over, and it is this quest that keeps the spirit of inquiry alive in the hearts of physicists and philosophers alike.